Hi everyone, this is Empawan from Data Science Branch, IARE College. Now I am here to explain you one topic called microprocessor memory management units. In this session, we are going to learn about what are the memory management units in the microprocessor. We will move on to next slides to learn about this. Introduction. This tutorial describes the current crop of commercial memory management units (MMUs) for 32-bit microprocessors. The discussion includes both complex and reduced instruction set computers (CISCs) and RISCs. So, the first session reviews the rational principles and related issues related to hardware support for memory management and virtual memory. And the second session contains brief overview of the following microprocessor units: Intel's 8086, i486, i486, i8, i860, Motorola 68851, MMU for the 68020, 68030, 68040, and 88200, MMU for the 88000 series, the Fujitsu MB86920, Spark MMU, and the MIPS R2000, R3000. So, in this session, we are going to see the microprocessor memory units, which include both complex and reduced instruction set computers for 32-bit microprocessors. So, we are going to segregate this into two sessions. The first session about the rational principles and issues related to hardware uh, support for managed memory and the virtual memory, and the second session about the brief overview of the microprocessor memory units. So we will move on to learn about it. Virtual memory management. So now we will discuss about this virtual memory management. Historically, the development of multitasking and multi-user system stored the need for memory management. Multitasking is essential. The multiplexing of CPU cycles among the tasks reduced in main memory to achieve a high overall resource utilization. In such systems, memory management must enforce isolation of distant address spaces to preserve the system's integrity. Protection fences established by the memory management hardware prevent the existing task for transgressing the boundaries of other tasks. At the same time, the memory manager must also allow controlled sharing of memory to support inter-task cooperation and synchronization. Sharing of code, such as in libraries and in common utilities, can result in a significant conservation of memory. So, what we are thinking is there are multitasking and in microprocessor there are so many multitasking and multi-user systems. So, for this, the memory management is the most important thing we need to look into it. Then the overall resources and what are the memory allocated for the task. Then the physical memory should not exceed the boundaries with other tasks. And to overcome this, all these things and issues, we are going to learn what are the memory managements are how they are managing for the inter-task cooperation and synchronization, and what are the inbuilt things they are doing. So we will move on next. Virtual memory is a memory management scheme distinguished by its capability to execute programs that exceed the size of available physical memory. The address space's size in a virtual memory system is limited only by the number of address bits that the processor can generate. Virtual memory operates by executing programs only particularly resident in memory while relying on hardware and the operating system to bring the missing items into the main memory when needed. Virtual memory systems are adaptive in the sense that the system dynamically allows an executing program to expand and fill the available spaces. In virtual memory systems, programmers are not restricted by memory size considerations, and the programs are portable between hardware environments with different memory capacities. So we are discussing about the virtual memory, which supports which gives the memory management which helps the memory management scheme and its ability to execute the exceed the size of available physical memory. When a task is exceeds the memory allocated to it in the physical memory, then those kind of tasks are done by the virtual memory. Virtual memory operates by executing programs only partially resident in memory. So in this way, it is a very beautiful option for us to execute programs. In virtual memory, programs are not restricted by memory size considerations. So the size of the memory is not at all an issue in virtual memory. The task will execute if the memory exceeds the physical memory allocated to it. That's the main thing the virtual memory does for us. Some implementations of virtual memory maps the entire operating system into the address space of each task. This approach results in protection of finer graduation and potentially increased efficiency because 1 or 0 and system calls do not have to cross the traditional user system boundaries. Means in virtual memory, one of the other main thing is the protection. It approaches results in protection. The way it executes gives us the fine protection for us in executing the code. Another advantage of virtual memory is that objects automatically migrate between the levels of memory, between the levels, between the levels of memory hierarchy on the basis of their frequency of reference. With virtual memory, the operating system has the added flexibility to control performance by varying the amount of real memory allocated to individual tasks. In any case, efficient implementation of virtual memory requires sufficient hardware assistance above and beyond that the basic underlying and memory management scheme. The clear separation of virtual addresses from physical addresses constitutes a key aspect of advanced forms of memory management. The system forms virtual addresses at program translation and are linked time. These addresses uniquely identify items that belong to one logical address space. This freedom is essentially to efficient memory management in multitasking and distributed systems in which tasks migrate in and out of main memory in response to state and load variations. Memory management hardware maps virtual addresses to physical addresses at runtime. The address translation hardware and the operating system cooperate in this process by using mapping tables. Memory management, address translation, and virtual memory. Virtual memory is a memory management scheme that allows execution of programs only partially resident in main memory is thus allows execution of programs those address spaces exceeds the size of the main memory available in the given system configuration. Since the operating system allocates memory dynamically at runtime, programs in systems with virtual memory cannot be bound to specific addresses at compile or link times. Instead, the systems prepare and store programs in executable files with addresses identifiers related to the beginning of each individual program. Another advantage of virtual memory is that objects automatically migrate between the levels of memory hierarchy on the basis of their frequency of references. The TCP is an operating system structure for task-related record keeping. Parts of the virtual address provide offsets into the corresponding levels of the address translation tree. An attractive aspect of dynamic addresses binding and runtime addresses translation is that address spaces of partially executed tasks may be dynamically reallocated in physical memory. Isolation is enforced by separating distance address spaces in physical memory and by ensuring that addresses transactions map each task virtual addresses and strictly into its designated areas of physical memory. Access control between stored in page descriptors provide the basis for protection and access control both input and between the address spaces. This is the thing we need to understand how the secondary storage works and how the memory is allocated. Just go through it, you can understand how the memory is allocated in the secondary storage and how the memory management unit works and how it goes in the level 1, level 2 pages and how the framework address is going on and physical addresses. And most of the things we can understand by dynamically and diagrammatically. We can easily understand these things. Memory management units. High-end microprocessors typically provide address translation logic and hardware assets as parts of their MMUs. Since the MMU maps virtual addresses to physical addresses, it must be placed between microprocessor emitted addresses lines and the physical memory addresses lines and a decoding circuitry. The MMU itself may reside on a separate chip, such as the 68851, or it may be integrated into the CPU chip or so that it can output physical addresses directly onto the processor address pins. This is one of the things from how the works from processor to MMU in virtual address. In physical address, it's physical address cache and physical address to main memory. This is one of the thing, and the other thing is from processor to virtual address, and virtual address divided to MMU and virtual address cache, then physical address to main memory. These are two kind of things, the MMU and cache placement in physical and virtual paths. How the MMU and cache placements takes place in these things. Physical caches prevalent in existing designs operate with physical addresses obtained after translation in MMU. Virtual caches, on the other hand, operate with virtual addresses. The primary advantage of virtual caches is the limitation of address translation overhead when the target item resides in the cache. Figure 2 illustrates the placement of physical and virtual caches in processor memory paths. A virtual cache uses virtual addresses and consequently must reside either on the processor or MMU chip. Physical caches thus provide potentially greater design freedom as larger caches may be incorporated into the system without imposing the real estate constraints of the single chip. Segmentation by virtual of subdividing an address space into logically related groups generally provides superior protection both within and between address spaces. Paging mechanically splits each address space into fixed size pages and allocates physical memory in same sized quanta called page frames. The strength of this schemes is that it can load pages belonging to a single logical object, such as an address space of an task, into non-contiguous pages frames in physical memory. Both segmentation and paging requires one paging table lookup per level of hierarchy in address translation. This reduces the effective memory bandwidth by 50% or more in the absence of hardware assets. This is one of the diagram of how the MMU and the address translation goes on in the way virtual memory, virtual address, and TLB, and all these things are in a cyclic process which happens in one task for the one task completion. You can understand it by observing the whole diagrammatic process. So we will move on next. Just go through it. You can easily understand with my explanation. Hardware support for virtual memory. The virtual memory specific aspects of address translation and MMU functionality include support for detection of missing items and hardware assistance to the operating system for page replacement. Most of these aspects come in the form of bits associated with each translation descriptor, such as segment and page descriptor. One byte of each page table entry is usually dedicated to indicate the absence or presence of the related page in main memory. This bit is often called valid or present. Some software sets this bit to reflect when the page related is locked into the physical memory. In general, this trade-off is technologically dependent and its outcome facilitates as the price and performance of individual components change. For instance, earlier implementations of paging favored larger page sizes mostly because of hardware support considerations. Unix considerations. The Unix operating system has a memory model whose implementation can be facilitated by making specific MMU provisions. These provisions include support for decontiguous in the virtual address spaces, space address spaces, and tracking of page usage history. Regions discontiguous in virtual address space and copy on write are much more efficient to implement with the hierarchical mapping tables shown in Figure 1 than they are with the more traditional linear or flat mapping tables. Unix uses a global page replacement algorithm that works better with the maintenance of larger page usage histories. It is therefore convenient for Unix implementations to have MMUs with support for the referend bit and provisions for storing the history of its change into TMT entries. Multiprocessor consideration. In multiprocessor systems with shared virtual memory and multiple MMUs, a mapping descriptor can be simultaneously cached in multiple TLBs. Since the contents of a mapping descriptor can vary in response to change of state in the related page in memory, multiple copies of a given descriptor may pose a consistency problem. As with caches, a crude way to deal with TLB coherence is to disallow TLB buffering of shareable descriptors, forcing all mappings to complete by using in-memory copy of a shared descriptor avoids the coherence problem at the cost of increased mapping delays. Consistency and coherence of shared entities in combined MMUs, cache or memory systems still pose an open research problem. If the past is an indicator, sometime will eclipse before a fate concurrent solution emerge and find their way into commercial implementation of cache and MMU units. I hope everyone understands this concept. Thank you for giving me this wonderful opportunity. Have a great day.